name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunication Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. Welcome to talk number 9 in the ITS RF Measurement Seminar Series. The talk today is measuring radar emissions, and when we left off last time we talked about what we need in front of a spectrum analyzer, namely a calibration source, a 0 to 70 dB RF attenuator, a filter section, and a low noise amplifier section, and we try to put all that as close to the measurement antenna as possible so that we can allow the gain and the low noise figure in the front end amplifier to overdrive the loss through the RF line going down to the measurement system. Today I'm going to draw out the basic way that we lay out the interior of one of our ITS RF front end boxes. We have one of these boxes sitting right here, and then in the lab session what we will do is actually use this box with this spectrum analyzer to measure an emission out of a radar, and we'll show an example of how we get the radar emission parameters that include its antenna pattern, its pulse repetition sequence, its pulse width, and its spectrum using the front end box. So, the first thing I'm going to do is draw out basically how we try to lay out a typical ITS RF front end, and this in a certain sense is our secret weapon in the war on radar spectrum. What we do, first of all, is allow for up to 5 antennas that we can have in our measurement system, and I'm going to draw them like this. And what we need to be able to do with the front end is be able to bring signal in from any of these antennas, like so, and at the front end we put a relay right here which can switch to any of these antenna inputs. And you might say, well, why do we want multiple antennas? Well, we want, for example, a high gain dish antenna so that we can get the highest possible signal to noise ratio in the measurement when we're actually doing the spectrum measurement. But we might also want to have an omnidirectional antenna so that we can get a 360-degree view electronically around our measurement site. We might also want a cavity-backed spiral antenna. That's what we're going to use for the lab session in this talk today, and I'll explain why later. And you never know what we might need for additional antennas, so we'll just call these auxiliaries. So, with that said, we have one other component that we need at the front end, and we want to have this component as close as possible up to the measurement antennas, and that is a calibration source, a noise diode. We talked about this a little bit last time. I'll do an entire talk about calibrating with noise diodes, but for now, just be aware that in the front end, we also have an input for a noise diode, which itself is powered with a 28 volt power supply, and this noise diode will be kept normally as a component inside the front end box. It's about so big I showed it in the last talk. So we can switch to the noise diode to do a calibration, and then we can switch to any of the antennas that we need to use to do the actual measurement. The next step in the sequence is to be able to go from that point through an RF attenuator, which itself can be switched to a value of anywhere from 0 to 70 dB. And remember that this is the place in our system where we achieve our wide dynamic range. The reason being that we can get up to 70 dB of RF attenuation here, plus 60 dB of instantaneous dynamic range in the spectrum analyzer that we're using, which equals a total of about, give or take, 130 dB of total available dynamic range in the measurement. Available dynamic range. Okay, like so. And we do this, as we said, by stepping our way through the spectrum. That's what we're going to demonstrate in the lab session today. Next, we need to be able to go through a front-end filter. And in our measurement systems where we build the boxes, we actually normally put in a whole array of such filters. We'll have one that's a yttrium iron garnet filter, which is a tunable bandpass filter. In fact, all of these are bandpass filters. We're going to label this BPF for bandpass filter tunable. And remember that the control voltage for this comes in from the spectrum analyzer, so that this knows, based upon a voltage that's something like 1 volt per gigahertz, and it does vary, but something like 1 volt per gigahertz, what its tune frequency needs to be. But in addition to having the YIG bandpass filter, which has an approximately 20 megahertz passband, that is, it allows our measurement system to see about 20 megahertz of spectrum at a time, it's also useful to have a set of fixed bandpass filters. And for that matter, a straight through path. And these fixed bandpass filters might, for example, go 0.5 to 1 gigahertz. I'll draw it like this. 0.5 to 1 gigahertz. And then 1 to 2 gigahertz. 2 to 4. And then 4 to 8. And in fact, I'm going to add one more here. And then we'll put the straight through path in. 8 to 18. We'll erase this little label just to make things a little more clear. Now, the idea is that if we're working with a radar signal, we'll probably need to go through the YIG path, because we need to be able, remember, to isolate the part of the radar spectrum that we're measuring right in here with the YIG passband right in here from the high power emission that we're not trying to measure when we're measuring out here in this part of the spectrum. However, in many cases, when we're doing other types of spectrum measurements, not measuring radars, but say doing spectrum surveys, what we may want to do is use one of these wider bandpass filters, because we can allow the measurement system to see a wide frequency range, maybe say from 2 to 4 gigahertz, because there are no strong signals in that entire range, and we're trying to make our measurement in that range. But we just want to limit the measurement system's front end from seeing strong signals outside the 2 to 4 range. Now you might say, but wait a minute, why not just use the YIG for all the measurements? Well, we could, but the YIG does have some limits. The YIG will not necessarily tune across the frequency range that we need to make a measurement in. And more to the point, the bandpass filters have a somewhat lower insertion loss. The YIG has, in fact, Randy, you could probably help me. What's the insertion loss on this YIG? Just approximately 6 dB?
Geez, you got me on the spot.
It's about...
I think the older ones had like 6 dB.
And this one's even a little better than 6 dB, right? Whereas a bandpass filter can have an insertion loss of maybe only 1 dB, half a dB, or maybe 2 dB at the most. So we can get a better sensitivity using a bandpass filter, as long as there are no strong signals in the bandpass frequency range, signals that are strong enough to overload the low noise amplifier that's going to follow this stage. So the way that we handle this is, in fact, to build a set of these filters into the box, and this box in fact has a set of filters like this in it, and then we wire these filters to a relay here, and I'm going to show the relay as being something that looks like this. And then we just bring the contacts out and down, out and over, and down and over, and all the way down. Oh, and sometimes we want to be able to look without any filter in front of our front end, in which case we can have a straight through path. And we've got just enough room for the straight through path here. So we can either go through a Yig filter, a set of bandpass filters, any one of a set of bandpass filters, or a straight through path. And then we build this thing symmetrically on the other side, like so. Bring it in. I'm going to jump over that line and come down like this. Come over like that, and this, and finally up and around and in like that. And then we put another relay in the system at this point so that we can contact any one of these switches. And then we have next, in red, a set of low noise amplifiers. Like so. And again, these low noise amplifiers can switch to, we can switch to any one of these. I'm not going to belabor it. You can see what the pattern is here. And we have a second switch here. And the reason that we have a set of these low noise amplifiers is so that, again, we can pick an amplifier which is especially well optimized. We might, in fact, have something like a 0.5 to 18 amplifier, something that's really wide, and then we might have some other amps that go something like 0.5 to 2, and then maybe 2 to 4, and then maybe 4 to 8, and then say 8 to 18. And then coming out of the amplifiers, we go through one last switch, like so. And the one last switch takes us out of the box and on to the rest of the measurement system, the spectrum analyzer in this case. And so we get the wide dynamic range with the attenuator. We get the pre-selection at this point in the measurement system with the set of bandpass filters in here. And then finally we get low noise figure at this stage in the system in the front end. And so we build the entire array into a box which, electrically speaking, has these boundaries from here all the way over to the edge of the board. Everything we have drawn in here, except for the set of antennas at the front end, is built inside the box. And you can see that basically this box consists of a set of relays. We'll let that go. Hate it when that happens. So the box consists of a set of relays. It consists of a set of discrete components between the relays, the attenuator, the set of bandpass filters, and the set of preamplifiers and a calibration source, a noise diode. The box also has control lines, it has sensing lines, it has some power supplies all built inside, and we do have to have control lines which control the relay settings. And we have to have a voltage line for the Yig control, and there are some ancillary lines that have to be wired in. And in the last talk, we looked at these boxes as part of the lab session. That takes care of what we have to put at the front end. One other thing that I want to talk about before we actually go ahead and measure radar emission as part of the lab session is how, when we're in a field location, we would actually position our measurement system, what we would actually do. typically when we're working in a field location, we're working with a measurement system that is configured inside an RF shielded box, which I'm going to draw like this. And the RF shielded box is built onto the back of a large truck, like so. And we have a couple of telescoping masts, like this, that go up and allow us to elevate a measurement antenna. And I'm exaggerating the size of the telescoping mast here, but on our current Premier measurement system, we have one of these masts mounted at the back. We have a second mast mounted on the other side of the vehicle at the front. We can put antennas on either one. Bear in mind, again, that we try to put, whenever possible, we try to put the measurement system RF front end, which I'm drawing schematically, as close to the antenna as possible, so that we can use that low noise preamplification inside the front end box to overdrive the line loss that's coming down and then through a carefully shielded port inside the measurement system, and which in turn goes into the measurement equipment right here, which includes, among other things, a spectrum analyzer, an oscilloscope, sometimes a vector signal analyzer, a PC computer to control everything, and so forth. And I'll do this with a little too small a wheel right there. All right. Now, well, I'll try to get this right because we're going to drive this forward, if you will. Now, bear in mind that when we're trying to get the wide dynamic range on the radar measurement, like this, where the spectrum is going to look like this, frequency, measured power, we're trying to get this, if possible, we're trying to get this power level up to as much as 130 dB above the measurement system noise floor. Here's the measurement system noise floor down here. We want to get that signal power level from a radar at least up as much as 130 dB out. Now, to do that, with most radars, even high-powered air traffic control radars, we have to try to get ourselves to a location on the ground with the measurement antenna where we get the highest possible power level coupled out of the radar, and where we're coupling the maximum power level into our system by picking an optimal antenna type. And so the antenna type that we will usually pick is a 1 meter diameter parabolic dish. The reason that we don't go bigger than a meter is it gets hard to mount a bigger antenna up there and have the mount be rigid enough and have the telescoping mast be rigid enough such that as the antenna pitches and yaws back and forth like this, the radar that we're trying to measure doesn't go out of the antenna beam. If we make the antenna bigger, the beam width gets tighter, and there will be a tendency as the antenna moves ever so slightly for the radar signal to get out of that beam a little bit, and that causes the power to fluctuate that we're measuring in the system. The other problem is that as the antenna gets bigger and therefore heavier, this whole system will in fact sway back and forth more, which exacerbates the problem of the radar going out of the antenna beam, never mind if something were to topple over. So 1 meter turns out to be a good trade-off between getting a high level of gain in the measurement system versus being able to keep the radar in the beam as the mast and the antenna mounts pitch and sway and yaw back and forth a little bit in the breeze. And and so that's that. Now, here is the next part of the problem, and I just alluded to it. I'm going to go ahead and erase this diagram. Just remember that we're trying to get to a place in the radar radiation pattern where we're getting the maximum possible amount of power. drawing this out schematically, we can imagine that we have an air traffic control radar located over here on top of a mast. And it's not unusual for airport surveillance radars or long-range air route surveillance radars to be mounted on towers or platforms which put the radar antenna at a height of about 80 feet above the ground, AGL, 80 feet above ground level. They'll have a great big antenna mounted up here. And this antenna is mounted on a rotating joint. And you might think that the place where you're going to get the maximum amount of power out of this antenna would be at the closest possible distance from the radar. In fact, people commonly think that the closer you come into a radar, the more power you're going to get. But there's a problem. And to explicate the problem, I'm going to redraw the measurement system with the mast at something that's a little more appropriate in terms of height scale. And to do that, we'll draw the mast first. If this is 80 feet, we can get our antenna on our system up to about typically 30 feet above ground level. So there's half of 80. So come a little below that and come out here like that. This is roughly the mounting configuration for our dish antenna on a mast mounted on the back of the box for our measurement system, like so. And so you see that we're a little bit below, typically we're a little bit below the radar height, and even if we tip our antenna up a little bit, what we're working against is the fact that this radar's radiation pattern looks basically like this. If it's an air traffic control radar, there will be a big lobe down here. There'll be some smaller lobes down here like this. And so as we move away from this radar, what we find is that we get lower power in close, and as we come out away from the radar, and we're measuring power level from the radar, and we'll assume that this radar rotates every 5 seconds. What we see is every 5 seconds as we're driving this system away from the radar, we see the radar look at us and we get a certain amount of power, and then 5 seconds later it looks at us and we get this power. 5 seconds later it looks at us and we get this much power as we're driving away. 5 seconds later here, and we see that we actually get more and more power as we're driving away from the radar. And the reason is because we're coming out into locations in the radar's radiation pattern where we're getting higher and higher coupling as we come out and away. So we keep driving, in effect, we keep driving forward, and we keep getting more and more power. And it turns out for most air traffic control radars, and this will vary for other types of radars, but for most ATC, air traffic control radars, we get maximum coupling, maximum power coupling, that is max power out of the radar, max power coupling occurs at distances between about 1/3 to 2/3 of a mile. Which is to say around 1 kilometer, give or take. When we get out about 1/3 to 2/3 of a mile, something at a distance of around 1 kilometer, we get maximum power into our measurement system. If we go beyond that distance, the power starts to drop off again just because of 1/r squared factors. So this is what we try to do, is get out into this kind of a distance range, and we actually will do a power measurement if we're in any doubt about it, where we actually will start driving away from the radar, and we actually will measure the power, and we'll see this power come in every 5 seconds, like so, as the radar looks in our direction, we'll actually trace that out, and we'll actually find a zone where we got maximum power, and we saw the power begin to drop off, and then we'll drive back into the middle of that zone and get ourselves set up for maximum power out. Now, for some other types of radars, for example, maritime surface search radars that have a beam aiming down, this distance is probably going to be substantially shorter. This distance might be just the distance across a parking lot, maybe 100 feet or 300 feet or 400 feet. So it depends upon the radar. But remember that the key, the goal here always is, and I've got the lack of hair to prove it, that we are trying to get the highest possible power level into our measurement system. And if at all possible, we'd like to get definitely 110 dB, and if possible, ideally, we'd like to get up to 130 dB of dynamic range on that measurement. And we do that by getting to an optimum location, we're getting the maximum power of the radar, and by using a parabolic dish antenna. Parabolic dish antenna. Typically about 1 meter, again, because that's a good trade-off in terms of gain versus the mechanical weight and size. Now for the lab today, which we're performing here at the lab in Boulder, we don't have the luxury of being able to put our mobile measurement system at an optimum distance from an air traffic control radar. Instead, we're going to couple the energy from an air traffic control radar that's about 30 miles from here into an antenna that's sitting in a window just outside this room. So we're not going to get this kind of dynamic range in the measurement, but we will use this as an opportunity to show how the stepped routine actually works with one of our RF front ends with our software that controls it, and we'll also look at how we get other mission parameters out of the radar. And so here are the parameters that we plan to measure out of the radar. We'll look at the antenna pattern, such as it is at this distance. We'll look at the pulse repetition sequence. We'll look at the pulse width. And finally, we'll look at the emission spectrum using the stepped algorithm. There, like so. One thing to note, the reason that we'll look at these parameters before we look at the emission spectrum is we need to know what bandwidth optimizes our signal-to-noise ratio in the measurement, and by looking at these two factors first, especially the pulse repetition sequence at the radar center frequency, we'll be able to determine the bandwidth empirically where we get the maximum signal-to-noise ratio. Remember from one of the earlier talks that theoretically this optimum bandwidth for the measurement of the spectrum occurs when the bandwidth is equal to about, or as close as possible, 1 over the pulse width of the radar. If it's got a simple pulsed CW emission, it will occur at a place where the bandwidth is equal to the square root of the chirp bandwidth divided by the pulse width if it's a radar that's chirping, that's FMing during the pulses, etc. For the lab today, we're just going to look at a radar that puts out very simple pulses where the optimum bandwidth is just equal to the nearest that we can come to 1 over the pulse width, but we'll actually go through that in the, as I say, in the lab session. So, at this point, we're about ready to transition into the lab. Are there any questions about what I've given you so far on these two boards before we transition into the lab session, the lab part? The demonstration part. All right. This concludes the whiteboard talk, the whiteboard part of talk number 9, and now we'll transition to the laboratory part. All right, this begins the lab session for talk number 9. This is where we will demonstrate the collection of a set of parameters on a radar emission. The parameters that we're going to look at will be the type of beam scanning the radar does, the time that it takes the radar to do one complete beam scan, the pulse sequencing in time, a measurement of the pulse width, and then finally a measurement of the radar's emission spectrum. In this part of the talk, we're actually measuring emissions from a radar that's located roughly 30 miles from our lab. So this is not an optimum location for the measurement, but it will demonstrate how we get the data. We're actually using a cavity-back spiral antenna in a window of our lab building about 20 feet away from where I'm standing. And initially, I'm going to show you what we see on a spectrum analyzer display. We'll then transition into the use of the computer-controlled system. This is what we would typically see if we were sitting somewhere near a radar. We're actually looking at the radar center frequency, which we've earlier established as being 2,760 megahertz, 2.76 gigahertz, and we're seeing the radar as it's looking at us every few seconds in time. This is a 0 hertz trace on a spectrum analyzer, so we're looking at what's happening in time across this trace, and we're looking in 5-second intervals. The sweep time on the spectrum analyzer right now is set to 5 seconds. Now, the bandwidth that we're looking at it with is 8 megahertz. This is probably not the optimum bandwidth to use. You remember in an earlier talk we said that we need to use a bandwidth that's as near as possible to 1 over the radar's pulse width so that we can optimize the dynamic range of the measurement. We'll check that by actually looking at this radar's power in 8 megahertz and in a succession of smaller bandwidths until we're able to actually reduce the amount of power that we're measuring. So take note now that we're at a reference level of minus 10 dBm. The radar's coming in at a power level of about minus 31 dB. So now we'll change the resolution bandwidth to a value of 5 megahertz. There we go. And we look at what's happening to the radar, and we have not lost any power. We're still measuring about minus 30, minus 31 dB. So now we go to a bandwidth of 3 megahertz, and we wait, and we're at about minus 31 or 32. So we might have lost a fraction of a dB, but nothing appreciable. But note that while we're not paying a penalty on the radar power here, we are getting a lower noise level over here because this noise level of the measurement system is dropping at the rate of 10 log of this bandwidth, and that means we're seeing more and more of the radar's rotational pattern. We're getting more dynamic range on the measurement. Now we'll take it down to a bandwidth of 1 megahertz, and we wait, and we get a slight reduction in power, about a dB. We're now down to about 32 to maybe minus 33 dB. dBm, I should say. Decibels relative to a milliwatt is what we're measuring here. All right, so at 1 megahertz, we may have paid a very slight penalty in measure power, but not more than about a dB. Now we'll take it down to a bandwidth of 300 kilohertz. Now we've dropped down to minus 20, 30, 40, minus 41, minus 42 dBm. So 300 kilohertz bandwidth is clearly substantially less than 1 over the pulse width. Now we are paying a penalty on dynamic range because this power level from the radar, as you'll remember from an earlier talk, drops as 20 log of the bandwidth, where the measurement system noise level drops as 10 log of the bandwidth. So that causes us to pay a penalty on the measurement system dynamic range. So we'll take the bandwidth back up to 1 megahertz, and this is the point where we get the optimum dynamic range, where the noise level is as low as it possibly can be relative to the power that we're getting out of the radar. Now, if this were an actual field site location, we would have also worked to optimize the measurement system's location on the ground, as I said earlier in the whiteboard section of the talk, and we would hopefully be getting about plus 30 dBm. Here, at this location, we're getting about minus 31, 32, 33 dBm. Now, having seen this, the next thing that we're going to do is look at how this radar scans in space. And to do that, we're going to go to a slightly longer sweep time. We're going to go to, let's say, we'll make it a 6-second sweep time. And then we're going to go to the single mode on the spectrum analyzer. And then I'm going to hit the single button and start the traces. And I watch to see what happens in the first interval. And I wait until I get the radar to hit me right in that first interval. There. Now we're going to get one complete rotation on the radar. Boom. Beautiful. The radar looked in our direction, some time elapsed and looked in our direction again. If we were to watch this radar over and over, we would find that this interval is always the same, and we're seeing no other beam scanning occurring in that interval, so we know that this radar has a simple mechanical rotation, and it probably has a 1 over cosecant squared fan beam radiation pattern, which tells us that it's probably an air search radar. Now we'll get its rotation time so that we can note it in our measurement notes, and for that we turn on a marker function. We go to peak search here, and then we go to marker delta, and then we find the next peak over, and the rotation interval turns out to be 4.61 seconds. So we would note that. This is a way of identifying radars. Even if a set of radars are all of the same model number, they'll typically vary ever so slightly in their actual rotation time, so 4.61 seconds. We note that, and at this point we would also record this scan, because this scan shows us the antenna radiation pattern at the location of our measurement system. We're not getting a lot of dynamic range on that 30 miles from the radar, but we are seeing some of those side lobe structures in the radar pattern here. Of course, we're also at this location seeing some multipath effects. But we would record this for antenna pattern and for antenna rotation time and for the beam scanning technique that the radar is using, because these all help us to identify what type of radar this is. They're also useful for spectrum management purposes. Next, we're going to look at what's happening right here, right inside the main beam of the radar in time. Now, air traffic control radars typically put out about 1,000 pulses per second. We know that they typically put about 20 pulses in the beam because that's where they get their optimum signal-to-noise ratio. So if we want to see what's going on inside the radiation pattern of this antenna right close to the point where it's looking at us, we want to go for a little more than a 20 millisecond interval. Let's look at about a 30 millisecond interval. And we want to trigger a sweep just as the radar is looking at us. So we're going to set a trigger threshold in here that's at about minus 35. So we go to trigger, video, and here we have a trigger threshold that's set not too bad, but we'll bring it up just a little bit. And now we'll go to single sweep mode. Now, we saw just the end of the pattern as it came around. We want to see the beginning, so we're going to go to trigger delay here of, whoops, going to go to a trigger delay on, go to a trigger delay of, say, minus 4 milliseconds. 1, 2, 3, 4 or so milliseconds. It's not terribly important. We get another sweep. It may take up to 5 seconds for the radar to look in our direction. Now we'll bring the trigger level down just slightly then. Okay, and single. There we go. Now we're seeing into the middle part of this radar's radiation pattern. In fact, let's take a maximum level pulse right here and count out until we're down 3 dB. And what I'm going to do is, in fact, go to peak search with the marker, go to normal. All right, and now we're going to go to delta, and we're going to go from that maximum level pulse out to a point where we're about 3 dB down, which is going to be about there. 1.49, not quite enough. Not quite there. We'll go back to this point where it's a little more than 3. Okay, there. Okay, that pulse is 2.7 dB below the peak. Now we're going to go to the next pulse over here that's equal to that amplitude. And that is going to be this pulse right here. There. Okay, those pulses are almost equal in amplitude. The time between them is 17.6 milliseconds. And these pulses are all within about 1.5 dB of each other. None of them are more than 3 dB down from the peak. This is where the radar is trying to really find a target. It's looking for a target right in there with those pulses. That should be about 15 to 20 pulses by radar theory from an earlier talk. Let's see how many it really is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Hit dead on. Okay, so they've optimized this. That's good to know. Basically, if you see the radar with 20, well, basically, if you can't see the radar with 20 pulses integrated in the receiver, you're not going to see it at all. That's what it amounts to. But if you substantially reduce the number of pulses, you do reduce the probability of seeing a target. So we know, again, that this radar is working in sort of conventional sense. Now, let's look carefully at the intervals between these pulses. The interval between these two pulses is 1.05 milliseconds. Now we go to marker normal, so that we're now on that second pulse, now delta, and we're going to get the time from the second pulse to the third pulse. 1.0 milliseconds, not the same interval as the first interval. Now we'll go back to normal on the third pulse, and now we'll get the time to go from the third pulse to the fourth pulse. So remember, 1.05 milliseconds, 1.0 milliseconds, 850 microseconds. All right, so now we have 3 intervals between these pulses, 1.05, 1.0, and 0.85 milliseconds. Now back to normal delta. Now we'll come and look at the interval to the next pulse in the sequence, 800 microseconds, all right. So now we have, 4 intervals that we've measured. Now we'll look at the next interval, 800 microseconds. Now the next interval after that, 850 microseconds. So we see that the intervals between these pulses are changing ever so slightly. They're on the order of a millisecond apart, but they're changing slightly. This tells us that the radar is utilizing a feature called stagger. Stagger means that the intervals between pulses in the sequence are not exactly equal to each other. The reason for doing this is to eliminate lines that would occur in the radar receiver if in fact the radar were transmitting pulses at an exact and non-varying interval. For example, if the radar were sending out exactly 1,000 pulses per second, you would get lines spaced exactly 1 kilohertz apart in the receiver. This is a problem if you're doing Doppler processing. In order to defeat or prevent those lines from occurring, you have to break up the intervals between the pulses such that the intervals between sets or pairs of pulses are not equal to each other and they're not even multiples of each other. And this is a technique that is used in air traffic control radars, which have so-called moving target indicator processing, which is Doppler processing. So the fact that this radar has stagger evident in the pulse sequence means that, again, it has moving target indicator, that is to say it's got Doppler processing. It's probably an air traffic control type radar because they're worried about using it to get velocities. All right, now we would note and we would record this pulse sequence as part of our measurement set on the radar, and we would note this so-called stagger sequence of intervals, which we could also play back out of the data later, having recorded it. Now let's zoom in one more time. Let's zoom in on an individual pulse inside the sequence and measure the pulse directly. We could, and oftentimes would, use an oscilloscope with a detector to measure this, but if you have to do a rough and ready job and you're in a hurry, you can go ahead and use a spectrum analyzer if it has a sufficiently short sweep time, which this one does. So what we're going to do is go to a sweep time of not 30 milliseconds, but rather a sweep time of 10 microseconds, because we're guessing that this pulse width is going to be about 1 microsecond because we optimized our dynamic range with a 1 megahertz bandwidth. So we determined, in fact, empirically that the pulses must be about a microsecond long. And now we'll go back to triggering, video triggering, and we'll actually bring the trigger, let's bring the trigger threshold up a little. We'll go to single, and we're going to need to do one more thing, which is to change this delay from 4 milliseconds to about 2 microseconds. Do that ever so quickly. 2 microseconds or so that we can see the beginning of the pulse. All right, take another trace. We might have to wait for up to 5 seconds. Now, we're in a 1 megahertz bandwidth, and we're seeing the effect that 1 megahertz bandwidth is actually rounding off the pulse shape. We need a little, here we want the widest possible bandwidth so that we can get the best possible resolution on the pulse shape. The widest bandwidth we have available is 8 megahertz. Boom. Now wait another 5 seconds, or less. Thought I did a symbol. Try it again. There, beautiful. And now we can use the marker, although I can see that because this is 10 microseconds across, which means 1 microsecond per division, this is about 1 microsecond long, but we can actually use the marker function here to look at that. There's that, and here's the other side of the marker, and what do we have? 933 nanoseconds, so it's about 0.9 microseconds pulse width. Okay, perfectly consistent with what we saw before. Again, we would record this information if we're doing a set of measurements. We would write down this pulse width, and if the radar were transmitting multiple pulse widths, we would get a set of these types of measurements. Now, having done all this, we're ready to run the actual spectrum measurement, the stepped algorithm measurement, and for that, we're going to go back to the bandwidth of 1 microsecond. We're going to verify that our detection is positive peak. We will go to a sweep time of 5 seconds, and the reason is the radar rotates every 4.6 seconds. So if we have the measurement system wait for an interval of 5 seconds, thank you very much, then we know that the radar will look in our direction every time we take a measurement point, and the radar is tuned to a center frequency of 2760. We don't have a lot of dynamic range available at this location, so we're going to measure across what, John? 80 megahertz total? All right, so go ahead. John Carroll here is going to actually perform the stepped measurement. And let's start this measurement. Let's start the measurement showing what the spectrum analyzer sees, and then we'll switch over to the computer at an appropriate time. Okay. So we're going to look at this 2 ways. We've only got 1 projector, so first we're going to look and see what the measurement algorithm, which is computer controlled, does to the spectrum analyzer. This analyzer is now running under computer control, or it will be, but it will be. It's going to tune to a particular frequency. It's going to sweep for 5 seconds. It's then going to pick off the highest amplitude point that occurred in the 5 seconds, correct it for a calibration factor, store that number and display it on a computer screen, and then step in frequency by an amount that's equal to our own resolution bandwidth. So that we're looking through a 1 megahertz window in width, and we're going to step that window, one window width, 1 megahertz, across, one point to the next. Right now we're still tuned to the radar center frequency, but ready. We're ready. This is a measurement system called RSMS4G for 4th generation. We're going to use antenna port number 1. Now we're not going to use the YIG here because the radar signal isn't strong enough to warrant using the YIG, so we're going to use a bandpass filter that goes from 2 to 4 gigahertz. This is our measurement system front end. As the computer understands it, we're going to come in through antenna port 1 on that box. We're going to go through that first relay position where we could calibrate with a noise diode. We're going to go through an attenuator, which is initially set to 0 dB. We're going to pass through this bandpass filter, and these are its characteristics. Then we're going to go through a low noise amplifier, and then we pass out of the front end box and into the spectrum analyzer. This is the nicest software that we've ever been able to implement. We've gotten better and better ever since the late 1970s when we started doing this. Now, this is the measurement. We're going to start at 2,720 megahertz. We're going to measure up to 2,800 megahertz. Remember that the radar is tuned to 2,760 megahertz. We're in a 1 megahertz bandwidth, and we need to take how many steps to go from 2,720 to 2,800 in a 1 megahertz bandwidth? Well, the difference between these two numbers is 80 megahertz. So if we're in a 1 megahertz bandwidth for the measurement, and we're going to go through 80 megahertz of spectrum, we need 80 steps. The math works out rather nicely on this.
Okay, now it's about attenuating.
All right, now, When the measurement system starts to run, it starts off initially with 70 dB of RF attenuation snapped, and we can see it over here, and it actually gradually reduces the amount of attenuation, looking for an attenuation level where it begins to see signal coming in. This is something that we have automated in this system that we used to have to do kind of manually. So it takes it a few seconds to find that nice attenuation level for the start. Now, we ourselves know right now that what we want is 0 dB attenuation, but as a general purpose solution, it's nicer to do it this way.
It's not setting it in for some reason. It went to 70, you can see it's a 70, but it's not stepping down.
All right.
Let's try it again.
For the purpose of the tape, we can edit this out.
Do you have any idea what's going on, Steve? The thoughts and the
I couldn't tell you. I thought you had it working.
Yeah, I had it working before when we started. It was working fine.
Okay.
Frank, you praised the RSMS software too soon.
Try to exceed the max attenuation check.
Yeah, but we're going to cut this part out on the tape.
How much time have you spent on the development of this stuff?
This has been going on for a few years now.
I'm trying to restart this.
In this particular software, yeah. Kill it. Kill it and start it over.
Restart this.
Well, of course, we turned it off and turned it back on, and that probably got it kind of confused.
We're doing everything now.
So again, we run the application there. Okay. Antenna port number 1, bandpass 2 to 4. Stepped. Okay. 2720 to 2800, 80 steps. Okay, I don't hear it switching the attenuator.
Let's try to exceed maximum attenuation check whether your RP using extreme type attenuator.
Tell you what, Jim, why don't you go ahead and stop the tape running? There's no use just wasting tape here. We'll get this, we'll pick it up again as soon as we can solve this. We'll cut out that last. Okay, and Bill Ingram, we had to put a delay in here while we had to take care of a software crash. We're now running again. So I'm going to stop talking, give you about 10 seconds, and then we'll just pick it up, and you can edit out everything up to this point where things were being problematic. Okay, so now what's happening is the spectrum analyzer is looking for an attenuation level that it can use where it is not overloading and where we can see the measurement system noise floor. So it starts off with a high attenuation level, it steps it down 60, 50, 40, we're still coming down. Basically, the algorithm looks for a point where either the overload flag is set in the spectrum analyzer or we hit 0 dB of attenuation. At this frequency, 2720, where the analyzer is working right now, it's going to hit 0 attenuation and not see the overload flag, and then it'll start the measurement with that level of attenuation invoked. All right, it's hit 0 dB of attenuation. It never saw the overload flag, so now it's taking a 5-second sweep at 2,720 megahertz. It pulls off the highest amplitude point in at 5 seconds, which turns out to be at minus 73.7 dBm. Then it steps by a frequency amount that equals the bandwidth, which is 1 megahertz. And so we saw about minus 73, then minus 75. Now we're seeing a level at that point of minus 64 roughly, and that may have been noise. Now we're going to see a point there at minus 66. Those could have been sort of stray noise points, or in this particular band they could have been, and they probably were, hits from a couple other radars in the area. They're probably very distant radars. I was watching them on the spectrum analyzer display in time, and I think there are a couple other radars really distant. Now what we're measuring is measurement system noise down here. This level down in here around about minus 77 in a 1 megahertz bandwidth, peak detected. We checked and we saw earlier, and you can't see it on the tape, that we are in fact getting the noise from the low noise amplifier in the measurement system front end into the spectrum analyzer at a level that exceeds the spectrum analyzer's own noise floor. So the noise figure of our overall measurement system, in other words, is being determined by the low noise amplifier at the front end. That's optimum, that's what we want. We're still seeing measurement system noise as we work our way across to 2,740 megahertz. This technique may look slow, but it's faster than doing maximum hold mode with peak detection in a spectrum analyzer. And as we've pointed out before, this allows us to get wider dynamic range because we can step the attenuation as we move along. That was another momentary hit from a source that was not the radar. And the reason I can say that is I'm watching the spectrum analyzer, which we can't actually see on the tape. So those are a couple other stray points. We're continuing to work our way along here. We're up to 2,749 megahertz. 2,750. The radar is tuned right here. We're going to come up about 40 dB as we approach 2,760. We're at 2,753 megahertz, 2,754. 2,755, 56. Now we're beginning to see the radar. I can see it on the spectrum analyzer display. 57. This is the radar coming in, the radar spectrum developing here. Here we go. 58. 59. The system's automatically adjusting the dynamic range on the display as we get higher level points out of the radar spectrum. Now we're coming down. This is an air traffic control radar that uses a klystron, which is itself filtered with what's called a diplex filter. So it's a very sharp emission spectrum on this radar. So we see that every 5 seconds we get a point on the spectrum on the computer display. That's a real feature in the radar spectrum right there. Little bump. Now we're coming back down into the measurement system noise floor. Now we're back down to the measurement system noise floor. We'll go ahead and run this out to 2800. Had this been a radar measurement in a good location and field, the dynamic range that we would have had here would have been at least 100, preferably 110, maybe as much as 120 to 130 dB. Here, as I said, we're only getting about 40 dB of dynamic range because of our measurement location, but our point in this part of the talk is to show how the measurement algorithm itself works. And I emphasize that if this radar were doing some complex frequency hopping, if it were doing complex beam scanning, it wouldn't make any difference to this measurement algorithm. We would get it just as well, just as long as we wait long enough for every single one of these measurement points. For a given radar, this could be anywhere from 1 or 2 seconds to as much as, for some weather radars, up to 1 minute per point. For most radars, it falls between 5 to 10 seconds per point. You notice that the way that it fills in the radar spectrum, we don't get any gaps. You will typically, with a positive peak detector running in maximum hold mode, get little gaps through here. That doesn't happen with a stepped algorithm because we methodically wait at each frequency for the radar to look at us. As I said, these points are not the radar emission. The reason we know that they're not the radar emission is I was actually able to watch the spectrum analyzer screen on each of these data points as it was developing the spectrum, and I saw that the emissions here looked like momentary pulses. They could either have been noise spikes or they could have been really distant radars. They were not this radar. And I could tell because I could see what was happening in the time domain as these points were taken. This screen over here bears mentioning. This shows us in real time what's happening on the spectrum analyzer display. We have some other nice features in the software. We can see whether on any given point we hit overload according to the IF monitor and the spectrum analyzer. This is a warning about YIG alignment. We're not using the YIG here for this measurement today. And then this green light shows us when the spectrum analyzer is itself actually sweeping. So it sweeps for 5 seconds, pulls off the maximum point in 5 seconds, corrects the point for calibration, plots, it steps to the next frequency, and runs across the frequency range designated in frequency step sizes that are just equal to the bandwidth that we're using. In this case, 1 megahertz bandwidth equals 1 megahertz step sizes, and now we're finished with this particular demonstration radar measurement. So at this point, having demonstrated how the measurement system works, are there any questions? All right, well, thanks for sitting in on talk number 9 in the RF Measurement Seminar Series.